There it is. All right, nerds. There it is. There it is. For an act of divine will, the announcements have been destroyed. Now I'm reading the announcements. So I'm going to read you the announcements real quick. Your warm-up, while the announcements are being read by yours truly, is right there. Your job is to figure out how much of the area of the total square is taken up by the red, taken up by the green, taken up by the yellow. Yes? Yes, go. It's not here. Yes, go ahead. You can guess, but you can also prove it algebraically. How much of the area of the square is taken up by the red, taken up by the green, taken up by the yellow? What's your guess? It's a good guess. You would think that, wouldn't you? Yeah, you would. There are 7 red squares here. It's really hard to see the 7th one. There are 7 green squares, and there are 7 yellow squares. Okay? Yeah, I know. It's kind of hard to see. We're going to stop at 7. Okay? It does technically go on to infinity. All righty. Don't want to see Miss Cook? Nope. All righty. Announcements read by yours truly. Oh, did I delete him? Hold on 1 second. Announcements, here we go. Listen up. Breakfast tomorrow will be scrambled eggs, a sausage patty, juice, fruit, and milk. Lunch today is a breaded chicken patty. Baked fries, broccoli/ranch, disgusting. Fruit and milk. Congratulations to the girls' swimming team. They earned first place at the East Moline Invite this weekend. They swim at Clinton tonight against Clinton and Davenport Central. Good luck, ladies. College visiting, Sauk Valley Community College on 10/11. So today's the 7th, so 4 days from now. Sauk Valley's going to be here. Educators of Beauty will be here on 10/18, so you got a little while before that. And Eureka College on 10/24. Please pick up a form in the office, meet up with these reps. I swear to God, Ms. Mitchell Johnson, if you highlight these and delete them. Okay. All right. Seniors, you can start filling out your FAFSA form as of October 1st. So guess what? You're already 6 days behind for being early. Please do not delay in doing so, as the grant money runs out quickly. If you're going to go on any type of education after high school, you must complete the FAFSA form. Seriously, do that. Okay? Do that. Don't end up in $100,000 debt like me, even that was after my FAFSA. But still, go do it. If you are interested in attending Theater Fest with the Drama Club this January, whoa, we're getting ahead of it. All forms are due tomorrow. Please pick up one from Miss Berglund if you have not already. Attention juniors and seniors, Morrison High School's prom committee will meet Mr. Bartos's classroom. That's who does everything. Room 6 on Tuesday, October 8th. That's tomorrow. During homeroom to discuss and select the theme for Morrison High School's 2020 prom. The prom will be held on Saturday, April 25th, 2020 at Deer Valley Golf Club. All interested juniors and seniors are welcome to offer their input and vote on the theme during Tuesday's meeting. So juniors and seniors only. So like none of y'all, except for a few of you. Josh, Jenna, thank you. There will be a boys basketball meeting on October 8th during homeroom in the cafeteria. All you should skip it because none of you have any skill. Boys basketball is looking for 2 students to video games and help out with different things. Please come to the office for more information. So they mean like record, not video games. It just came out funny. All girls interested in playing girls basketball this year should attend a players meeting during homeroom on Friday, October 11th in the chemistry lab. Happy birthday today to no one. Don't forget to stop into the Bi-County room to pick up your free DQ treat. I don't know what that means, but it sounds nice. Bailey, no crying. It's ice cream. It's ice cream, Bailey. Just think about it. Everyone loves ice cream. Me too. What's your favorite kind? Respect. Quote of the week. If you have the chance to make people happy, just do it! Just do it! sometimes people are struggling silently. Maybe your act of kindness can make their day. Should I edit it?
Yes.
I feel like I should. One of these days I'm going to edit the quote of the day. We're just going to see who reads it. Don't tell no one. Okay? I'm going to make something real good. Semper Ubisoft. Alright. Okay. Yeah, we'll keep it innocent. So yeah, it's your warm-up. Song of the day is dedicated to someone in particular, but mostly all of you. It's called Super Stupid by Funkadelic. It is a band created by George Clinton and his groups from Parliament. It's Funkadelic because it is funk music combined with psychedelia. Super Stupid from the album Maggot Brain. You've seen the album cover on my screen. I know you have. It's the lady that's buried up to her neck in dirt, screaming. Maggot Brain is a fantastic guitar solo, probably one of the best of all time. Guitarist Eddie Hazel, and I believe the lead singer is this Eddie Hazel as well on Super Stupid. Here it is. If you need to make up a quiz or a test, order in Friday. Get in here.
Super stupid, what if I said bad? Thought it was cool, but it was scared.
time. So, your warm-up. Bailey, whom we do not trust, although she does like the same ice cream as me. That's got to count for something. Says that it should be a third. The red part is a third, the green part is a third, the yellow part is a third. Well, let's figure that out. So, infinity. What a So we said 7 squares, right? Something like this. Quadrats, that's 2. There's 3. There's 4, and on and on and on. I believe that this was yellow. I also believe that this was green. Right, and then we got some more in here, which I'm not going to color in. And then red. All right, so hard problem, right? So what if we had it be easier? How much is the red out of this entire square if I just ignore the rest of the red? It's a quarter, right? Right? 1/4 of the whole thing. Now, this square right here is a quarter as well, right? So I want a quarter of a quarter to figure out this area, right here. What's a quarter of a quarter? When we say of in mathematics, we mean multiplication. So when I say a quarter of a quarter, I'm saying a quarter times a quarter. We multiply across with an A, no cross multiplication in here. So across, it's 1/16. Okay, so that guy is 1/16. This guy's a quarter. Well, this guy. It's a quarter of a 16th. Well, a quarter of a 16th. What's 4 times 16? 4 times 16? Hard question, easier question. 4 times 16 is the same thing as 4 times 8 times 2, right? What's 4 times 2? What's 8 times 8? Play with your numbers. Find an easier way to solve the problem. How are you, Ellie? No bueno? Because of this or something else? Okay. How was homecoming, everybody?
Boring.
Boring. Trash. Yeah, that's what I keep hearing from all my classes. So y'all are morons and followed me on the IG, my math account, right? Hey, I posted like 2 things. And then you were dumb enough to let me follow you back, right? Which of course I had to do because the clout, right? I mean, that's what it's all about. You give me clout, I got to give you clout back, right? Respect. Got to respect the game, respect the hustle. I ain't no dummy. So I followed you back, and then you accepted me. So I got to see all your pictures, which first of all, gross, right? Like, I don't want to see that. Second of all, it was like a little bit like, oh, it's my babies. They're all growing up. It's just like, you're all my kids, you know. And what's really funny is when I see you hanging out with kids from other classes that I teach, and I go, wait a minute, they're friends? Then I always think, like, you could do better. You could do better. A lot of you guys could do better. A lot of you guys. Some of you guys, you're hitting out of your league, okay? But others, you could do a lot better, okay? Consider that. Yeah, that was fun. Just seeing that pop up on the little TL, right? So we got 1/64 here is we get. So that's what this guy is. So now we're 3 squares deep into this squareception. Next thing is going to be 1 over what? What's 64 times 4? Let's do it in our heads. Sort of in our heads. Let's do 60 times 4 first. That's 240. Now, I wanted 64 times 4. That's 64 groups of 4. I only did 60 groups of 4. How many more groups of 4 do I need? 4 more groups of 4, which we know is 16. So together we're going to get 256. Right? All right, now we're 4 squares deep, going into 5. 256 times 4. Let's estimate that in our head. Instead of 256, let's do 250 times 4. What's 250 times 4? 1,000 Well, I needed 6 more groups of 4, right? Because I underestimated. I only did 250 times 4. I need 256 times 4. What's 4 times 6? 24. So I'm going to get 1024, aren't I? So now we're 5 squares deep. $1,024 times 4. Well, what's 1,000 times 4? 4,000. So we're sitting at 4,000. And then I need to do 24 times 4 in my head. Well, I can do that. What's 20 times 4? 80. What's 4 times 4? Add them together. 96. 4096. Last square, because we only wanted to go 7 deep, right? We need 4,096 times 4. What's 4,000 times 4? 16,000. Now we need 96 more groups of 4. Let's estimate that. I'm going to round up. Instead of 96 groups of 4, let's do 100 groups of 4 in our head. 400! I shot over by 4 groups of 4, so I shot over by 16. So really it's 84 when we pull that back by 16. You dig? Try this again. 96 times 4. Let's estimate that in our heads. We're going to round up. Instead of 96, we're going to do what? 100. What's 100 times 4? 400. But I overshot by 4 groups of 4, right? So I overshot by 16. What's 400 minus 16? Not 84, but 384. Right? We were at 400. We subtracted 16. I was nice and had mercy upon you. My other classes, I just let them sit there in that. They were so confused for so long. What's my first rule? We've been over this in here? Rule number 1. My rules. I don't have many. More like guidelines. Rule number 1. Trust no one. What's rule number 2? Have we really not talked about this in here? No Natalie today. Have a plan to kill everyone you know. It's good to be prepared. We'll keep it at 2 rules today. Have you not been writing down like everything I've said since the beginning of the year? There are a lot of good quotes. Missed opportunity. All right, so snitches get stitches, by the way. So here we are. Chance, when I looked over, Chance was like, I don't know her. I've never. You and everyone you know. Jenna. No, I love Jenna. I've never said that aloud, but I do love Jenna. Jenna's great. Bailey, on the other hand, the anti-Jenna. All right. So we're going to add all these up. What do we need to add up fractions? Let's think about it. So if I've got a half plus 3/4, can I just add across and get 4/6? How do you know that's wrong? Tell me why you know that's wrong. Hannah. Yeah, but like, why does that matter? Yep, that's not going to cut it. Because my teacher told me so. Yeah. Rule number 1. Trust no one. Hannah. Shh. What?
I'm a piece of scum.
Never have I connected with you more, Hannah. All right. We can't do it, but why? How do we know that can't be right? How do you know? Look at it. What does it mean? How do you know that can't be right? A half plus 3/4 is 4/6. It is. Why? How do you know?
Not in a simple form.
2/3? Okay, we can do that. Yeah, that's valid. So how do we know that this should not equal 2/3? Come on.
There we go.
Use your brains. Oh, now it's all good. Chances like now it's right. Nope.
That bothers me.
Calvin. I'm going to say what he meant to say, at least what I heard. 3/4 is more than 2/3. Right? I thought that's what you said. I just couldn't hear very well. 3/4 is more than 2/3. And so we're adding a half to it, and we're getting 2/3. Another way to think about that is half plus 3/4. Is 3/4 more than a half? Yeah, so we've got a half plus more than a half. It's going to be more than 1. How do we get less than 1? You dingus. Can't be right. There's no possible way. So that algorithm of we just add a cross can't be a real algorithm, right? So we need common denominators, right, Hannah? Yeah, common denominators. So what that means is we look at the bottom and they got to match, right? So we've got a 2 and a 4 on the bottom there. So how many quarters are in a half? 2 quarters. So I can rewrite that like this. And 2 divided by 4 is still a half, right? We didn't change anything. It's just a different way of looking at it. How many quarters do I have now? 5 quarters. Because I've got 2 quarters, you got 3 quarters, and now we have 5 quarters. Ellie! Yes, you may. I hope you feel better, Ellie. Whatever happened, you don't deserve it. Was it Marissa's fault?
It always is.
Probably. It's so funny when I get to see you guys hanging out with people outside of this class with like other kids, other classes, and I go, man, y'all could do better. All right, so here we are, 5 quarters. That was efficient. Okay, so we're sitting at 5 quarters, right? How do we get common denominators for these guys? Yikes, right? Okay, so check it out. When we did it before, we figured out how many quarters are in a half because quarters is the smallest thing, right? Quarter's smaller than a half. It's more pieces. So what's our smallest fraction here? Very good. 1 out of 16,384. That's the smallest one. So how are we going to get that fraction to have common denominators of that one? How many 16,384ths are in 1 4,096? Oh, you don't know? Come on, guys. There's 4 16,384ths in 1 4,906 or 96. How do I know that? Well, how did I get this number to begin with? I multiplied the bottom by 4, right? We already did the work. Oh, isn't that great? Okay. This one, when I change it to common denominators, I get the bottom number for free because I'm trying to make it look like that. I don't need to do like, okay, what's 4,000? What's 16 times 1,024? Oh, okay, good, right? That's why we're doing it. Take the win. Now, I multiplied this guy by 4 to get to here, right? And I multiplied this guy by 4 to get to there. That's how I got 4,096. So I multiplied by 4 twice. Do not say we're going to multiply by 8. We're not multiplying by 4 and then multiplying by 2. We're multiplying by 4 and then multiplying by 4. If I multiply by 4 twice, it's like multiplying by 4 squared, right? What's 4 squared? Fun game to play outside. What is it numerically? 16. So we're multiplying by 16. So there are 16 16,384ths and 1 1,024. Oh. How many 16,384ths are in 1 over 256? Well, I got to multiply by 4 to get it to look like that, then get it to look like that, then get it to look like that. So I'm multiplying by 4 cubed. What's 4 cubed? What's 4 times 4 times 4? What's 16 times 4? What is 16 times 4? What is 16 times 4? It's the same thing as 4 times 8 times 2, which is the same thing as 8 times 8, which is 64. So I multiply by 64 to get there. So I'd multiply the top by 64, and now I'm here. So now we're 4 deep. 1, 2, 3, 4. I need 1 over 64 converted to 16,384ths. How many 16,384ths are in 1/64? Well, I got to multiply by 4, and then by 4, and then by 4, and then by 4. What's 64 times 4? Oh, wait, didn't we already do that here and here? It's 256. Do you see the pattern now? 1, 4, 16, 64, 256. 1, 4, 16, 64, 256. Next one's going to be 1024 over 16, 384. because it's going to be 16 times 4 times 4 times 4 times 4 times 4, right? We already know what 16 times 64 is. What's this? Last one. How many 16,384ths are there in a quadra? Macy can't even see anything, and she knows. Wow. Full disclosure. Shout out to Preston. I'll do this. Last year I had Preston in my class. Preston is deaf. So when I said shout out to Preston, I realized you can't hear me, but maybe closed captions are on, so I'll just wave. Preston was the Macy of last year. Preston can't even hear and he knows what's going on, right? Shout out to Preston. That guy's awesome. Great chess player. Very funny guy. I joke about his deafness only because that is the only joke he knows how to tell. Everything relates back to his ears. Hi, I'm Preston, I'm deaf. Ha 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 ha. That was how he introduced himself. Weird kid. All right, so now we're here. Miss you, Preston. Let's add them all up. Well, the denominator is going to be 16,384, right? Let's add up some numbers. Let's make some easy ones. How about 4 and 256? What do they add up to? $260. What about 16 and 1024? What's going to be 10 something? What? 40. 10 4 0. These aren't as nice, but let's add them up. Be 4,000 something. What's 64 and 96 together? What's 60 and 90 together? 150. What's 4 and 6 together? 10. So 160. Yeah. Great. And then we have 1, right? Don't forget about 1. And 1. Add them up. 1. 6 carry the 1. 4, 5. Yes or no? What a song of the day. It me. Five, four, six, one. Check out. Well, right here is 1,300, right? 1,300 and 4,160 makes 5, 4, 6, 1. Yeah. Okay. So, you said it was going to be a third, right, Bailey? So this should be the area of all the reds, right? That's red, that's red. We added up all the reds. And you said it should be a third. Bailey! Does this simplify to a third? Bailey. How can we check if it goes to a third? Yeah. Can you do that? Because you didn't do any work earlier because you're like, it's a third, I'm done. So now you're going to do a little bit of work just to check. Take your time. Oh, it does. What's the decimal that you got?
0.33.
Whoa, 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 whoa. How many threes?
4.
And then what?
1, 2, 9, 9.
That's not a third. That's a little bit less than a third. That's not a third. No, a third would be 0.3 repeating. It's a little bit less. What? Bailey, you're wrong. Sort of. Why is it less than a third? That is the question, I think. All right, we have the answer. No one cares about the answer. The question is why. Why is the red area less than a third? Ellie.
Those are black lines.
The lines take a little bit of room? That is a wonderful conjecture. We're going to assume that the black lines are negligible and have no thickness. But that's a really good point. Like in real life, yes, that would be true. That's why when you go to cut boards, right? I think we talked about this in here, maybe not in here, maybe in other classes. Right? When you cut it, you have to think about the width of the saw to actually pick stuff off. Which is why when you buy a 2x4, it's not actually 2 inches by 4 inches. It's more like 1.5 by 3.5. Because by the time they sand it all down, width of the blade, it's not really a 2x4. Which is annoying when you're like building stuff. Like, look at those. Put 2x4s down, like my dad did when he built the deck for the first time. And he's like, why am I always too short? Well, because they're not actually 2x4. It's just not as fun to say 1.5 by 3.5. So no, lines are negligible. No saw width. With the D in there, it's hard for me to say. Why? Anybody dance at homecoming? Watched New Girl for the first time last night. Watched the first season. Nick Miller is the love of my life. It's all good. They did the chicken dance in slow-mo. That's my move. He is me. I'm debating whether to watch any more of the show. I feel like TV steals my ideas all the time and I get no credit for it. All right, anyway. Why is it less than a third? Where are your gods now? You seen the cat meme where he's on top of the pole? I see no gods up here. Y'all not know memes? Okay, fair enough. Fair enough. Bailey, got an explanation for us? Yeah, that's what I thought. Aye.
Is it that really small square at the top?
This goes on into infinity. So it's going to get closer and closer and closer to a third. The more tiny we get, right? But there's always going to be a little bit left over. This is back to the 0.999999 repeating equals one thing, right? This is a third. It's just going to get closer the further we go. We stopped at 7 squares. 1, 2, 3, 4, 5, 6, 7. But there's a lot more. And the more squares we keep adding on, the closer we are going to get to a third. So yeah, it's a third. Because you learned something today, that's why. Yeah, you did. You learned how to get kami danamis. Everybody loves kami danamis. Put it away. I want you to draw me a picture. So get out some paper.
Yay.
Shut up. All hail Derek, really? Really? Sorry, I was harassing one of my students that wasn't paying attention. Well, it's not okay, but I'm glad you understand. Yeah? Rad. Are you the Cinderella of the story? Is that what's happening here? Draw me a picture. Two parallel lines being cut by another line. When we have two lines being cut by another one, I'm not a crook. When we have two lines being cut by another one, what do we call that line, that red line? What do we call it? What do we call it? Oh, you can't see it. That's funny. Shut up, Hannah. Hannah's always saying stuff. Bailey, did you used to have braces? Like recently? That makes a lot of sense. Do you have friends now, or do you still, like, don't? I'm sorry. Did you used to think it was because of the braces? Because now we know definitively that's not the case. Yikes, that sucks. Someone be Bailey's friend. Yikes, you guys deserve each other. All right, here we go. Hannah, what's your favorite kind of ice cream? Vanilla?
She's allergic to chocolate.
I'm gonna be honest. Respect to vanilla. Respect. 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 Like, I'm trying to be mean and antagonistic here to them because, like, I can never admit that I actually enjoy my students. I have to hate them because that's the character I play on TV. But I gotta respect vanilla. I gotta. What do we call a line that's cut by two others? Or another way of saying it, two lines that are cut by one. What do we call that red line right there? No, bisect means to cut in two. Perfectly. These are infinite lines. Yeah, sure, whatever. Why did I call it T? Sounds like a wrestling move. Come on! Nope. A line that cuts two others. What do we call it? Talked about it last time. No. Half. Call it a transversal. Sounds like a wrestling move, but it ain't. Transversal is a line that cuts two others. Now, if those two lines happen to be parallel, which they is in this diagram, we know something special about these angles. Label your angles like this, please. Last time we watched a spooky YouTube video about people that ended up in the same location, right? So when I say relative location, I'm not talking about the same location. I'm talking about the same general idea, right? Relatively to the same location. So for instance, angle 1 and angle 5, if you label them correctly like I did, are in the same relative spot. They're both in the top left corner. See the intersection? Top left corner of that intersection is angle 1. See the intersection? Top left corner of that intersection is angle 5. Yes, ma'am? Yeah, I thought I gave it to my third hour and my first hour classes, and then they got mad at me because I didn't. And I kept insisting that I did, and it was you guys I gave it to, wasn't it? Yep, okay. Well, I wanted it to be due Friday, but it can be due this Friday, okay? The bins aren't even back there. All right, so pro move. Your hair is so long. Yeah, it's very nice. All right, 1 and 5 are corresponding angles. We call them that. Remember, cap was the postulate that we talked about. So corresponding angles are angles that are in the same relative position. They correspond. They go together. Now, when these lines are, in fact, parallel, not only are they just like, oh, they're just corresponding angles, right? But it actually, by corresponding angles postulate, cap, remember the red cap? That poor kid. They're actually congruent. Now, this is only true if these two lines are parallel. Otherwise, they're just corresponding angles. But corresponding angles postulate says if they're corresponding and those are parallel, then they're congruent. Cool, great, wonderful, fantastic. All right, so you'll notice that when we have this diagram, we have an outside and an inside. We have inside the parallel lines, we have outside the parallel lines. When I talk about inside, I'm talking about internal. Outside, I'm talking about what? Nelly! Yes. So when I talk about inside the parallel lines, I'm talking about internal. When I'm talking about outside, what's the word for that? External, very good. So here's an external. And here's the external, the outside, right? And the inside we call internal, which I'll do in light green. So internal is the stuff in between here and here. And the external is the stuff between here and infinity. Right? Cool. So when I say, give me an example of an external angle, Quinn, give me an example of an external angle. 7. Yay, it's external. Landry, give me an example of an internal angle. 3, indeed. Name all 4 internal angles, Chance.
Internal?
The internal.
3, 6,
And?
4,
And?
5.
Yeah, buddy.
Hell yeah.
Yeah, there we go. All right, so we got Chance engaged. All right. So here we are. The other angles are the external, right? There's also 2 sides of this transversal. We have the left side and we have the right side. You see it? The left side angles are 1, 4, 5, and 8. They're on the same side of the transversal. The right side angles are 2, 3, 6, and 7. They're on the same side of the transversal as well. So we have 2 ways to talk about angles, external and internal, and we have same side, right? So let's talk about some angles. Let's talk about same side. Oh, as opposed to same side, they could be opposite sides, right? So like 4 and 5 are same side, but 4 and 6 are opposite sides. Another word for opposite is alternate. We're going to be using that. Alternate or alternate means to switch back and forth. So 4 and 6 are alternate angles. They're on opposite sides of the transversal. You dig? Cool. First type of angle we're going to talk about is alternate interior angles. So alternate interior angles are alternate because they're on opposite sides of the transversal. They're interior because they're inside the parallels. You dig? Congrats to the Cardinals. Wainwright, man. 38. Still a beast. An absolute beast. I was there for the first time he won the World Series for us. It was amazing. I got bored after because we just kept winning so many, and I switched to being a Blues fan. So I used to be a Cardinals fan. Give me examples of alternate interior angles.
On there.
Yeah.
3. Wait, no.
And?
6. Wait, no, 3 and 4. I don't know.
3
I don't know.
and 5. It's all good. It's all good. 3 and 5 are alternate interior because they're on opposite sides and the interior. Now, you might say, well, what about 3 and 4? They're on opposite sides in the interior. I know. Isn't that screwy? Those are also alternate interior angles, I suppose. But they're not as interesting. Because if you notice, 3 and 5, when the lines are parallel, what do we know about 3 and 5? What does it look like? They're congruent, aren't they? Whereas 3 and 4 are not. They're a linear pair. We ignore ones that are right next to each other adjacent because we just say, those are a linear pair. Period. That's it. We don't call them anything else. Okay? So 3 and 5 are alternate interior. Cool. And there's a theorem that says if we have parallel lines, then the alternate interior angles that are created by them are going to be congruent. So alternate interior angles theorem, I should say. We're going to talk about that in a second. Let's get some more angles. You'll also notice that 4 and 6 are also alternate interior angles to each other, right? Crisscross applesauce. Let's talk about alternate exterior angles. Mark! Give me an example of an alternate exterior angle set.
2 and 8.
2 and 8 are alternate because they're on opposite sides of the transversal, and they're also in the exterior, right? So that's a win. So 2 and 8 go together. Alternate exterior angles. Landry, give me the other 2.
1 and 7.
Mm-hmm. Oh, yeah. Those are examples of alternate exterior angles. Cool. Now here's the problem. I'll bring it up later. How about, we've talked about both the alternate versions, interior and exterior. Let's talk about same side. We'll start with same side interior. Ellie, give me an example of angles that are on the same side and are in the interior.
5 and 4.
Very good. 5 and 4 are same side interior because they're on the same side of the transversal and they're in the interior, right? Jenna, give me another example of same side interior angles. They need to be on the same side and be in the interior. Already said 4 and 5. 3 and 6. They're on the same side of the transversal, right? Here's the transversal, the red line. They're both on the right side of it, so they're on the same side. And they're in the interior, right? Here's the exterior. Here's the interior. Good. No yawning in math class. I believe in you. I know you would. Let's just save us the trouble, okay? All right. How about same side exterior? Marissa, same side exterior. Give me an example.
1 and 8.
Yeah. 1 and 8. 1 and 8. Nellie, give me an example of another two. She was thinking of it ahead of time. Way to go. All right, so that's the basic rundown. We have alternate and interior. I'm sorry, interior and exterior. We have alternate and same side. 4 different combinations we can do there. We're going to talk about the theorems behind them later. We don't have time for that today. You do need to know CAP, corresponding angles postulate. It says that if these guys are parallel, then corresponding angles are all going to be equal. Okay? You should hang on to this diagram. There's one last thing we need to talk about. Two things, actually. Let's talk about vertical angles. Who remembers what vertical angles are? What? Scissors. Scissor theorem. Your words, not mine. It's when two angles are created by two intersecting lines. Any two intersecting lines. No matter how they intersect, the two angles always scissor each other. Check this out. This angle and this angle here, both the same. If I change the angle that I have the lines intersect, notice those guys are still the same, right? If I change it to be like this, same angle top and bottom. Top and bottom are always the same. Same thing with the sides, right? It's kind of hard to tell with these scissors because they have a bend in them. But yeah, those are the same angles. Those are the same angles. They're still the same angles. So whenever we have an intersection, the top angles are always going to be equal. Same thing with the side angles. Scissor theorem. Vertical angles. These two are the same. Those two are the same. Always, doesn't matter if they're parallel or not. It's just whenever you have two intersecting lines. Top angle's the same. Always. Side angles are always the same. Always. That's vertical angles. Last thing. Hannah. I said her name backwards. Hannah, 1 and 2 are an example of what? They are collinear. However, we don't use that term for things other than points. Mark, help her out. They're a linear pair. It's the thing no one can ever remember. Linear meaning line, pair meaning two. Yep, I understand. I know why you say collinear. I totally get that. Technically, if we had 5 angles on a line, they would all be collinear. But they wouldn't have the special property of being a linear pair. You see what I'm saying? Okay. And then by linear pair theorem, we know that linear pairs are always what? 180 or supplementary, right? Vertical angles are always congruent. Linear pairs are always supplementary. Nice. Okay. So tomorrow we're going to talk about alternate interior angles theorem, alternate external angles theorem, if there is one. Same side interior angles theorem, same side external angles theorem, etc., etc., etc. And we're going to prove that certain angles are congruent, certain angles are supplementary. You better bet that's going to be your quiz on Friday. We might even play a game on Wednesday, because it is a half day. I don't know. Don't care. I stay here the full time. That's what we're going to do. Hang on to this diagram. See you later. Freedom fundraising. Can't have freedom without capitalism. Bye. Wasn't talking to you, Hannah.